Provide an example of a relation which is reflexive and symmetric but not transitive. Number 2, reflexive and transitive but not symmetric. Then number 3, symmetric and transitive but not reflexive. Okay, let us begin. So here we'll start with the first one. We'll try to define a relation which is going to be reflexive and symmetric, but it is not going to be transitive. So let us suppose that let R be a relation on A. Now when we say that R is a relation on A, this simply means that the relation R is going to be a subset of the Cartesian product of the set A with itself. That is what we mean. So here we will suppose that let the set A consist of 3 elements, the element 4, the element 6 and the element 8. And we have the relation R. So let's say the relation R, this is going to be a set containing ordered pairs. So let's say it contains the ordered pairs 4, 4, 6, 6. Then we have 8, 8. Next we have 6, 4. Next 4, 6. Then 6, 8. And we have 8, 6. Right. So this is the relation R which is defined on the set A. Now we will show that this particular relation is a reflexive and symmetric relation, but it is not going to be transitive. Now clearly the definition for reflexive states that R is reflexive. A given relation R is going to be reflexive if and only if we have the ordered pair A, A belonging to the relation R for all values of A belonging to the set A. That means any element that we pick up from that set A, the ordered pair A, A must be present in the relation. So in our case, if we pick up the element 4, then the ordered pair 4, 4 is present in the relation. If we consider the next element which is 6 from the set A, then we have the ordered pair 6, 6 present in the relation. And then finally, if we pick up the third element 8, so we also have 8, 8, the ordered pair present in the relation. That means all the elements of the set A, which is 4, 6 and 8, these have the corresponding ordered pairs 4, 4, 6, 6 and 8, 8 present in the relation. So here clearly R is a reflexive relation. Okay, next we'll show that R is also a symmetric relation. Now symmetric means that if we have the ordered pair A, B belonging to the relation R, then this must imply that the ordered pair B, A must also belong to the relation R for all values of A and B belonging to the set A. That means we pick up 2 elements at random from the set A, and then if we form the ordered pair A, B belonging to the relation R, it must be true that interchanging the position of the element, so A, B becomes B, A. If that element is also present in the relation R, then the relation R automatically becomes symmetric. This implies that R is symmetric in nature. We have symmetry. Okay, so let's verify whether our relation R is symmetric or not. So if we have 4, 4, then interchanging the elements within the parentheses, so we are going to still get 4, 4. So we don't have to check for the first 3 elements. It's quite trivial to say that 6, 6 is present, then interchanging the elements in the ordered pair also gives us 6, 6 which is present in the relation. So let's go to the 4th ordered pair. So 6, 4, if we pick up this ordered pair, then 4, 6 is present in the ordered pair. Or we can go the other way around. If we pick up the ordered pair 4, 6 present in the relation R, then 6, 4 must also be present, and we see that it is definitely present. Then if we consider the last 2 ordered pairs, so if we have 6, 8, then 8, 6 is present, or if we consider 8, 6, then 6, 8 is also present in the relation. So here clearly R is a symmetric relation. However, R is not going to be a transitive relation. The reason behind this is, let's look at the definition first. If A, B, the ordered pair belongs to the relation R, and B, C belongs to the relation R, it belongs to the relation R, then it must imply that A, C must belong to the relation R. Then for all values of A, B and C belonging to the set A. then in that case we say that our relation R is transitive. Our relation R is transitive. Now for our case, so if we pick up the element 4, 6 and 6, 8, so let's pick this two elements. So 4, 6 belongs to the relation R and 6, 8 belongs to the relation R. So here we are picking up these two ordered pair in a very specific manner. So here the second element of the first ordered pair, which is 6, must match with the first element of the second ordered pair, that's also 6. So where 4, 6 belonging to R and 6, 8 belonging to R must imply that 4, 8 belongs to the relation R. However, there is no such ordered pair belonging to the relation R. So here we will say that the ordered pair 4, 8 does not belong to R, and this is telling us that the relation R cannot be transitive. So R is not a transitive relation. So for this particular example, where the set A is given by the elements 4, 6 and 8, R is the following set of ordered pairs. This relation R is going to be reflexive, it is going to be symmetric, but it is not going to be transitive. Now let's go to the second problem, where we have to provide an example of a relation which is reflexive and transitive but not symmetric. So here also let's consider a relation S. So let S be a relation, relation on some set B. Let's call it the set B, and is defined as we have to define the relation, and it is defined as the set S containing the set of ordered pairs A, B such that A is less than or equals to B, where A and B are elements that belong to the set B. Fine. Now, is the relation S reflexive? Let's verify that. Let us consider an arbitrary element A belonging to the set B such that if we consider A, A belonging to the relation S, according to the definition of the relation, A is greater than or equals to A. All we are doing here is replacing B with A. So is A greater than or equals to A? That's a true statement. So this implies that our given relation S is reflexive. This is a reflexive relation. Then we are going to consider two elements A, B. These two elements are picked up from the set B such that if we consider the element A, B belonging to the set B, this implies that A is greater than or equals to B. That's the definition. But by no means can we say that B is greater than or equals to A. This is not a true statement. B cannot be greater than or equals to A provided A is greater than or equals to B. But this is telling us that the relation S is not symmetric. This is not a symmetric relation. Okay, so we have shown that S is reflexive, but it is not symmetric. Now finally we will check whether if it is transitive or not. So for this we are going to consider three elements. So let's say we have A, B and C. All of these three elements belong to the set B such that if we consider A, B belonging to the relation R and B, C belonging to the relation R, but simply implies that A is greater than or equals to B and we have B greater than or equals to C. We're using the definition of the relation. Now A greater than B and B greater than C, we can also combine it and say that A is greater than B is greater than C. Or simply put, we can say A is simply greater than or equals to C. Now A greater than or equals to C, this is coming in our definition. That means A, C belongs to the relation R. So we started out by considering the ordered pair A, B and the ordered pair B, C belonging to R, and we are successfully able to show that the ordered pair A, C also belongs to R. So this is telling us that the relation R is transitive in nature. So here what we have done, we have taken this particular example where S is a set of ordered pairs A, B such that A is greater than or equals to B. We were able to show that the S is reflexive, it is transitive, but it is not symmetric. Okay, now let's come to the final one, the third part, where we have to show or we have to give an example of a relation that is symmetric and transitive, but it is not reflexive. So we begin by considering a set A containing two elements. Let those two elements be 1 and 2. And we are going to consider a relation R which is on the set A containing the ordered pairs 1, 1. We have 1, 2, then 2, 1. Fine. Now clearly the relation R is not going to be a reflexive relation, because reflexivity demands that if we pick up any element from that set A, then that means for 1, if we pick up the element 1 belonging to the set A, it must imply that the ordered pair 1 comma 1 must belong to the relation R. So this is working, so this is fine. However, if we pick up the second element, which is 2, so 2 belonging to A, implies that the ordered pair 2 comma 2 does not belong to the relation R. So because of this, we can say that the relation R is not reflexive. This is not a reflexive relation. However, it is going to be symmetric as well as transitive. So let's check for its symmetry first. So for symmetry, what we'll do? So for the ordered pair 1 comma 2, we don't have to worry about 1 comma 1. So 1 comma 1 is very trivial. We'll only check for 1 comma 2. So for 1 comma 2 belonging to the relation R, so we see that 2 comma 1 also belongs to the relation R. So this tells us that R is symmetric. So this is a symmetric relation on the set A. And then if we then we'll finally check for transitivity. So for 1 comma 2 belonging to the relation R and 2 comma 1 belonging to the relation R, it immediately tells us that 1 comma 1 also belongs to the relation R. So here we can say that our given R, the given relation R, is transitive as well. So here, with the help of this example, we have shown that the relation R on A is going to be symmetric and transitive, but is not going to be reflexive relation.